Good to be here. Thank you for that introduction, Olga. So today we'll be talking about kind of intermediate to advanced R topics. So I'm going to be assuming that most of you have some prior programming experience with R, having at least used R for some kinds of analyses and probably writing your own R scripts, maybe you've written some functions, maybe not, but you're familiar with R, all of the basic uses of R, and you kind of want to take a little bit of a next step to understand how to write functions, write better functions, and some more advanced things like how to write faster functions, how to use R's object-oriented programming systems, and things like that. So we have kind of five major topics that we'll be going through today. So we'll be starting with a little bit of reproducible research stuff. So this isn't necessarily strictly R stuff, but it's some topics that'll kind of generally help you as a programmer, as a developer in organizing and making sure that the code that you write in R or in other languages is reproducible, and you can easily share it with other people and keep in sync between different developers and that kind of thing. Next, we'll be talking about functions and how to write good functions, R's functional programming style. We'll talk about the object-oriented programming systems in R, so S3 and S4. And then we'll talk a bit about performance, so some of the things that go into writing faster R functions and how to benchmark that kind of thing. And then lastly, we'll end with some scalability topics, so things like how to parallelize your R functions and work with data that might not fit into memory.
Kylie, there is a question. Do we need to install some packages in advance for today's session?
So just a second. Yes, if you want to follow through all of the code that we'll be working through. I don't remember if I have a list of what should be installed, but we'll kind of be working through that as we go along. So for the most part, a lot of things can be installed along the way. But a lot of the things that we'll be doing will also be kind of more general R coding things rather than using some specific packages. But and the main thing for right now is that you are working with a recent version of R, so that would be R for version 4 or greater, and a recent version of bioconductors. So I think that would be 13 or something or greater. I have that on the Google Doc, I believe. Okay, so we'll start by talking about some reproducible research topics. So all of the material for this is available online. Hopefully you can find a link to that through the website. If not, maybe a TA can share it in the chat as well. For some reason, my Q&A thing isn't showing up in the proper screen. All right, so, all right. For some reason, whenever I try to check the Q&A, I need to go to a different screen to do that. So bear with me if I do that. If I see a question, I'll go over and check it. And if there's any questions that I don't see or kind of seem to be missing, a TA can speak up and let me know. Especially if there's any questions on YouTube. I know we have some, may have some people watching on YouTube. So the TAs can please watch for the questions there and let me know if there's anything. All right, so we'll start by talking about reproducible research. So we're going to start by talking about R Markdown. Then we'll talk about Git and GitHub. So R Markdown, many of you might already be familiar with R Markdown and what it is, but to kind of motivate why we are talking about R Markdown. So whenever you're using R for analysis, oftentimes you get some very good results. You want to turn those results into some kind of report, whether that's as some kind of supplementary material for a publication, or just to show people, collaborators, or things like that. So you're writing some kind of R analysis, and you want to turn that analysis into some kind of report or presentation. And if you want to do that, another goal that's a part of this is that that analysis should be reproducible, and the document, whether that's a report or a presentation or some kind of dashboard even, that should also be reproducible. So ideally, we can have some kind of report that can be updated if we say get new data, and we want to create an updated report that includes that new data, or if we change the data set, or if we change something in the analysis, that we can very easily create a new report that reflects either that new data or those changes in analyses without having to go in and change everything manually. For example, if the analysis was in a Word document, so we don't have to go through and copy over new figures and things like that. So all of this should be easily automated and reproducible, so that if we change a data set or the analysis, we can create a report that reflects that as well. And so this is where the idea of R Markdown comes in. So R Markdown is a format that combines R with the Markdown markup language. So R, as you know, is it's the R that you're familiar with. So R Markdown allows you to prepare a neatly formatted report that includes R code as part of it. So we have R code chunks. We can have inline results and figures that are produced directly by those R code chunks. And if we ever make any changes to either the input data set or the analysis code, we can just rerun this R Markdown document to create a new updated report. What Markdown is if you've heard of LaTeX, Markdown is very similar to LaTeX, but much simpler to use. So Markdown is a markup language, which means it's a language that you use to format text. So essentially, you're coding a document very similarly to how you use R to code an analysis. So you use R to code your statistical analysis, and then Markdown to format the report or presentation that you're creating. And then you can export these documents to PDF or HTML or various other output formats. So the purpose of R Markdown is to be able to turn R code into some kind of high quality reports. If you've ever looked at the vignettes from an R package, and I'm sure all of you have, they're a very useful way of learning how to get started with an R package. All of those, well, many of those are now written using R Markdown. So we can use Markdown to format text, R code chunks to write code and get inline results that show up in the report, and we can compile all of this together into some kind of professional quality document. And then whenever the analysis changes or whenever the data changes, we can recompile all of this to produce an updated report. Working with R Markdown from our studio is fairly simple. So I'm going to go over to our studio here. So we go to the New button and create a new R Markdown document. Then we just give it some kind of title, my R Markdown document, an author name, that's you, and then some kind of output format. So the most common being either HTML or PDF. And you can see we can also produce other kinds of documents. So a document would just be like your normal report. We could create a presentation. We can even create some kinds of interactive dashboards if you're familiar with the Shiny R package. But we'll start with just a basic PDF report. And so using RStudio to create an R Markdown document, we get a nice template. So a lot of things are already set up for us. So at the beginning of an R Markdown document, we have some header material that describes what that document is. So the title, the author, a date, and the output format. So this is a PDF document. And then we can have R code chunks. So wherever we want to include R code or run some kind of R code in our document, we can just include that surrounded by 3 backticks. And then curly braces and the letter R to indicate that this is an R code chunk. And then we can include some optional options after that if we want. So a name for the code chunk that just makes it easier to identify. If something goes wrong, if there's any errors, it makes it easy to figure out what code chunk that error was in. So here, this is just a name for this code chunk. It's called setup. This code chunk here is called cars. This one's called pressure. And then there's various other options that we can include in these R code chunks. So whether or not that code should be printed in the document or not, whether the results should be shown or hidden. So sometimes we might want to use a code chunk just to run some code in the background that we're going to use later in the document, things like this. So here is just a simple code chunk, for example, summarizing some of the built-in data sets that come with R. And then here we have some example of Markdown formatted text. So in our Markdown document, we have our code chunks, and we also have Markdown formatted text so that you can include whatever commentary write-up that you want in your report or presentation. So Markdown is relatively simple. So for example, here we have 2 pound signs or octothorpes or hashtags, whatever you want to call this symbol. And that just indicates some kind of title. You can see here we can use asterisks or underscores to indicate either bold or italicized. So for example, here is a brief example of some of the different kinds of formatting that we can use with Markdown. So italics or underscores let us create italics or bold. We can create subscripts, superscripts, different kinds of headers, lists, much more than this. And then the nice thing about all of this is that we can then create a document just by clicking this knit button. So if you're in RStudio, once you have an R Markdown document and you want to see what the finished document would look like, you can click this knit button. If you're working outside of RStudio, it's a little bit more than that. You can use an R function. I believe it's called render in the R Markdown package to do this. So first I need to save this. I'll just call it test.rmd. And we can see that some things are running. And now it's showing me the final R Markdown document. So here we have a PDF document. You can see the different formatting that has been applied through the markup language, the Markdown markup language that we've used. And you can see we have inline R code along with the results of that R code. So here we have an inline plot that we produced from our R code as well. Looks like there's a question. Let's see. Maybe the TAs can answer these questions. For the first one, maybe a TA can help with the LaTeX installation question. As for R notebooks, I actually haven't really used those extensively. So if a TA is more familiar with using R notebooks, maybe they can answer that one as well.
Kylie, if you don't mind reading questions next time, because people on YouTube don't get to see the
Oh, sure.
Q&A.
So one question is about R notebooks. So R notebooks are something kind of similar to an R Markdown document. I actually haven't used R notebooks extensively enough to be able to recommend when to use them, but I believe R notebooks, if they're anything like Jupyter notebooks or things like that, which I believe was the inspiration, are kind of more for easy interactive analysis that might be a little bit more dynamic and easily organized than writing a standard R script. So I believe an R notebook is kind of more for nicely formatted interactive analyses, whereas an R Markdown document is more something that's going to produce a static document that can still be updated whenever you have new data or change the analysis. But I think the idea is an R Markdown document is more for sharing with people who aren't going to be necessarily running that analysis themselves, whereas an R notebook is a little bit more geared toward interactive analysis and things like that. But if a TA is more familiar with that, maybe they can add something. Then there's another question about LaTeX installation that I believe Sai is answering. So that's R Markdown. So there are some the code that we'll be working through today is in R Markdown. So I've shared the R Markdown part of that. Those can be knitted to an HTML document if you have the appropriate packages installed. So typically RStudio will say at the top if you need to install any packages for that, but we'll be working through some of those, the code in those R Markdown documents together today. And so just kind of to summarize, the purpose of R Markdown is to be able to produce nicely formatted reports and documents from some kind of statistical analysis that you've written in R in a way that we can easily update and produce new versions of those documents whenever we've changed the analysis or get new data. And so this is a very useful technology for anyone who cares about reproducible research. So if you want to provide code in supplementary material for a publication, R Markdown makes it a very nice way to share that code in a way that makes it easy for other people to actually see what you did more easily than just a standard R script, because you can have a nicely formatted report with inline figures and commentary through the Markdown formatting and things like this.
Kylie, there's a question of general nature. Could you comment on R versus Python in general and for mass spectrometry-based applications?
Okay, so well, that's kind of a big question. So R versus Python. I think in general for statistical analyses, that's kind of what R is really designed for. So for anything where you're really doing a statistical analysis, where you're interested in doing some kind of statistical modeling, especially linear modeling or mixed modeling, and you're interested in statistical results, comparisons, that kind of thing, I think R really has the advantage there in terms of being the lingua franca of statistics and statistical analysis. Many of the packages in R are written by the people who developed those statistical methods in the first place. So there's often many of the publications that develop new methods for statistical analysis have an associated R package. So the MS Stats group is a great example of that. My own Cardinal package as well for analyzing mass spec imaging, or MS Stats for analyzing proteomics data. When it comes to Python, Python is a more general purpose programming language. So it was developed as a general purpose programming language without the focus on data analysis that R was. That being said, in the last decade or so, Python has become very popular among data scientists and for data analysis. So through NumPy, scikit-learn, pandas, and all of these things, there is a lot more available in Python now for analysis. I've not really used it myself for analyzing proteomics data or mass spectrometry data, so I can't comment on that specifically, but Python is especially useful if you're trying to, say, automate some kind of workflow, perhaps on the cloud or something like that. So generally speaking, I think if you're just trying to do some sort of statistical analysis, R is the place to start with that. And if you are trying to communicate among different programming languages, working with different kinds of APIs, and combine that with the analysis that you're doing, so automating some kind of analysis on a large scale, then Python can sometimes be more appropriate for that. So I guess that would be my the main commentary that I would make. In terms of performance, things like that, I would say that there's no real difference. Both R and Python have their places that they're slow and places that they're fast. We'll talk more about that later, especially with regards to R. But I guess that would be my suggestions in terms of Python versus R.
Kylie, there's a question regarding the usage of rCloud for today's section. Can participants use rCloud instead of RStudio for today? And if yes, is there any R projects to use?
I would think that they should be able to use rCloud. I haven't prepared any specific projects for rCloud. So in the past, I've created this material generally assuming people would be working on their own computers, but you should be able to use rCloud, I believe. I'm not sure if users have permission to install packages or not, but I think a lot of what's completely necessary should be there. But certainly for a lot of the material, it should be the same regardless. And a lot of much of the material we'll be going through doesn't require any external packages. We'll get to some material that does, but a lot of it doesn't really require external packages. So for the most part, using rCloud should be fine. Let me check any other questions. Okay, I'll leave the questions there for the TAs. Some more comments on R Markdown. So there are some more advanced options that you can use with R Markdown. So you can customize code chunks. We saw some examples of that. So you can decide whether you want the code chunks to be echoed in the document. So if you want the code to show up or not, or maybe you only want the results to show up. You can do things like setting dimensions of plots and many other options that you can set for the different code chunks. RStudio has a very good kind of cheat sheet for R Markdown that's very helpful for when you start using it or just whenever you forget what some of the common either options are for the various code chunks or different Markdown formatting options. So I have a link to that here. So if I follow this, here we have a nice cheat sheet showing a lot of the different options. So some questions again on knitting. So using a PDF output for R Markdown does require a LaTeX installation. If you use HTML, it should not require a LaTeX installation. But if you want to have a PDF output, then you need a LaTeX installation. So that is R Markdown. Any general questions about R Markdown. We move on. So we'll see some more R Markdown documents throughout the day as we work through some of the coding examples together. All right, so we'll move on to Git and GitHub. So as we just said, we want our analyses to be reproducible. And let me request to share the link to this in chat so I can do that. So I've shared a link to the cheat sheet in chat. If you're using RStudio as well, there's actually under help in RStudio. If you go down to cheat sheets, there's a link. There are links to a number of very useful cheat sheets directly through the RStudio interface. So in RStudio, if you go to help, down to cheat sheets, here's the R Markdown cheat sheet. There's also useful ones for a lot of different RStudio packages, as well as the RStudio IDE itself. So here's a link to that cheat sheet through RStudio. All right, so we want our analyses to be reproducible, and and we also work through various versions of our analyses. So when we're coding, or even when we're working on a publication, oftentimes the first version is not the best one, and we need to go through many revisions, many edits. That's especially true with coding and writing analyses. So we also might want to do different kinds of analyses, try different options, and we might want to kind of keep track of the different versions or different steps of the analyses that we've done. So a common problem that comes up with this is, how do we actually manage our files, our different R code source files, or even different files in terms of writing a publication, whether that's in R Markdown, LaTeX, or whatever you're using to author it. So kind of a typical way of managing this kind of problem is you have, say, a Word document, you think you're finished, then you share it with your collaborators, you get some revisions that you need to do, you save a new version, but you want to make sure you have the old version as well. So you give them different names and so on and so forth. And eventually you have a folder full of different versions of the same document, and you're not really sure which one is which, or things like that. So this is where version control comes in. So version control is a way of managing complex projects that produce many files. So this is going to be the case, especially with any kind of programming. So when you're writing R code for an analyses, lots of times you might have different versions of that source file, or you might be writing different source files, different R code files for different kinds of analyses, for different data sets and that kind of thing. And you want to be able to track changes between these different files, be able to track the different versions, and be able to go back and compare the different versions to understand what has changed. Also, ideally, this makes it easy to, you want to make it easy to share with your collaborators, and have your collaborators also be able to see what has changed between different versions, and make those changes yourself, themselves. There's some comments about the link in RStudio being broken. So if for some reason that doesn't work, try the links in chat. It looks like the link that I shared earlier didn't work, since there was a formatting issue, I guess, when I pasted it in. So Sai has pasted a new link that should work. So version control is this way that we can track changes between many files. So the goals of a version control system is to track the different changes made to a project. We want to be able to track changes across multiple files, so not just a single file. So if you're familiar with something like track changes in Word, typically that's just for a single document. But if you have a kind of a complex project where you're doing different kinds of analyses or working with different data sets, then you might have different R code files that you want to all track together. So a version control system allows us to track changes across multiple files. We want to be able to track creation and deletion of files. So if we delete a file that was for a particular analysis we thought we didn't need anymore, but then we realized we did need it, we might want to go back and be able to restore that file. And we also want to be able to easily go back to earlier versions or merge changes between different files if we want to. Another goal is to be able to have multiple what we call branches of progress. So say you're working on either an analysis, or maybe you've gotten to the point where you're working on some kind of R package yourself or an R script that contains many different functions that people in your lab might use. And maybe you might have different versions of this, or you're working on a new feature and you don't want that to be confused with the version that has a stable version of all of those functions, or a stable version of that R package. So then we can have what we call multiple branches, where we have a stable version that you share with people that they can use that version. And then you might have other branches where you're working on a new feature or a fix to a bug, and you can make edits to those branches without worrying that you'll make a change that breaks something in this stable version of your project. We also want to be able to synchronize work with collaborators. So we want to be able to have our collaborators make changes to these files and be able to see those changes ourselves and have all of this be tracked between us. Check on questions very quickly. Question, does R Markdown support interactive data reviewing or link to outside data sources? I would kind of have to see some elaboration on that, but I believe you can create a dashboard version that allows some interactivity. So if you're familiar with the Shiny package in R, you can embed things like Shiny widgets. As for linking to outside data sources, you would have, if you're using a package that allows you to access external data sources, then you could do that. R Markdown itself doesn't have any specific facilities for that kind of thing. So R Markdown just allows us to embed R code in a document. But there are many R packages that might allow you to, say, work with data resources that might be on the cloud somewhere. So if you're using a package that allows you to do that, then you could still use that code in the R Markdown document. Looks like there's a question in chat as well. I'm running very long analyses for proteomics. I save each in a different project in a different folder. How can I use Markdown in regards to 2 different R projects? So firstly, again, to echo TA, if you have questions, please use the Q&A feature so we can more easily track those. But as to answer that question, R Markdown doesn't particularly care where the data actually lives. So as long as you have the file path to where that data exists, then everything should work fine. So yeah, so I think that's, if that doesn't answer that, let me know. But R Markdown itself, just as long as it's just a way of embedding R code in your document, so it doesn't really matter where the data lives. As long as your R code can find the data, then everything should work. To return to version control. So a little bit of vocabulary before we talk about a specific version control system, namely Git. So When we talk about version control systems, we usually talk about what we call repositories. If you visited a GitHub site for a package, you've probably seen a repository. So a repository is just basically a place that stores a project tracked by version control, as well as the history of that project, so all of the changes that have been made. So a repository or a repo just stores a project that is tracked by a version control system. We have what we call a commit in a version control system. A commit is essentially a snapshot of a set of changes. So whenever we make changes and we kind of want to save our place or make a snapshot of the current state of our project, we do what we call commit. We make a commit of those changes. A project in a repository has what we call the head. So if you see references to the head of a version control system, the head is just the most recent commit. So when you're working with Git, as we will in a moment, and you see references to the head of the repository, that just means the most recent commit, essentially. And then when it comes to sharing and synchronizing work with collaborators, we do what we call either push changes to another repository or pull changes from another repository to our own. So if we have collaborators, we might push the changes that we make to our collaborators, and we would pull the changes that they have made into our own repository. So in terms of how a version control system works, a repository has a history, so it tracks all of the different changes, well, specifically all of the different commits that we've made. And so we can go back to earlier revisions, earlier commits whenever we want. This is essentially represented as a kind of graph. So we have links between the different commits that we've made. Different commits rely on earlier commits. So we can backtrack kind of through the history of our project. And as we said, we might have different branches. So we could potentially have different branches of development where we have kind of one branch where we're working on a new feature or a different version of our analysis. And then we have another branch that is kind of the stable version that we would share with people. And the idea is these different branches are different versions of the same project, but we can work on the different branches independently without worrying that we might break something in another branch. And then we can merge changes between these different branches if we want. All right, so let's talk about a specific version control system. So Git is a very popular version control system. It is what we call a distributed version control system, which means that it doesn't rely on one central repository. Instead, everyone has a full-fledged Git repository on their computer. And we could also have one remote on, say, a site like GitHub. So Git doesn't rely on one central repository. Instead, everyone's own Git repository is a full-fledged version control system on its own. So each repo is fully, what we say, mirrored on each developer's machine. So we each have a full, complete version of the repository. So that is Git. We'll talk more about it in a moment. And then there is GitHub. So I just want to make it clear that Git and GitHub are different things. So Git is just the version control software that we use to track changes. GitHub is a website that hosts online Git repositories. So GitHub is a very popular place to host Git repositories for free for open source projects. And using a GitHub Git repository makes it easy to share work with collaborators, because then you can kind of use that GitHub repository as a central place to store kind of the main version of your project, and you can use that to push and pull changes between you and your collaborators. So if you don't already have Git installed, you can follow these links to install it. If you're on Mac OS, usually there should be a version of Git installed already. If you're on Windows, I'm not sure. You may need to install it. If you are on Mac, for example, if you just open a terminal window and type git, if you see some kind of options or a help page like this that you're seeing on my computer right now, that means git is installed. If it says command not recognized or something like that, then you need to go install git. So we'll be talking about the command line version of git. There are GUIs or graphical user interfaces for working with Git, but we'll be talking about the command line version because it's going to be the one that's the same between any operating system, whereas you can get different graphical user interfaces for it, but the command line version is always the same. So if you've installed Git, you first need to kind of do some basic setup. So you can configure your credentials to tell Git who you are, since if you're making changes, a version control system needs to know who is making the changes. So it doesn't only track the changes that are made, it also tracks who made all of those different changes. So these would be the commands to set your username, your user email, and here I'll just show my own configuration right now. Let me make this a little bit larger. So maybe I'll do that. So if you can see down here, I'm just listing my own configuration. So I have my username and my user email set up like so. And so if you're using GitHub, for example, these would be the credentials that are also synced to GitHub. And so this is just a way that Git knows who is making the changes. So when you're working with collaborators, you can see who made a particular commit. Oops. Close this markdown document. So once we have Git installed and Git knows who we are, it's very simple to create a simple Git repository. So any directory or folder can be turned into a Git repository. So a Git repository is really just any folder that has a Git history in it. There's actually a hidden .git directory in any Git repository that stores all of the information that Git uses to track changes and history and things like that. So a very simple way of initializing a Git repository is to just type git init. So here I'm in my May Institute 2021 Intermediate R directory. So in terms of, if you want to see that is just a regular folder here. This is where I am in my terminal window. So I'm going to assume people have used potentially a terminal window before. So I can navigate among different files. So let me go back to the directory that I want to be in. So here I'm in my May Institute 2021 directory. Let me create a new directory. All right, so I've made a new directory called git test. You can see it showed up here. Question, is the same in Linux? Yes, so all of this should be the same in Linux. You can install it. In Linux, you probably already have Git installed, but if not, you can install it using whatever package manager your Linux system uses. Yes, so all of this will be the same across any operating system, which is why we're using the command line version, because this version will be the same regardless of operating system, whereas each operating system might have access to different graphical user interfaces. Is there another question? Question, what is the difference between using Git with the command prompt and Git bash? I'm actually not sure. So I've only ever used the standard Git command line version. So I've not used Git bash. I assume that's some specialized version of the Git command line system, but I'm not sure. So what I'm using is just the standard command line version of Git that you would get with any Git installation. Looks like there's another question. Just a comment that the person asking hadn't used Git bash either. I apologize for the constant flipping back and forth. I don't know why the Q&A only shows up on another desktop for me. So if you see me switching back and forth, I'm just going to check the Q&A. All right, so I've created a Git test directory. Let me change to that directory. There's nothing in it right now, but all I need to do to turn this into a Git repository is do git init, and that initializes this directory into an empty Git repository. And it doesn't look like there's anything in it. If I look at hidden files and directories, I can see that there's a hidden .git directory. And this is, you don't normally want to go in and look at this, but that hidden .git directory is just what Git uses to actually track all of the changes, track your history, store information about your commits, and all of that thing. So a Git repository is really just any directory with that hidden .git directory that Git uses to track changes and things like that. Now that we have this as a Git repository, I can do things like, so now I've created a simple text file. I'll show you more on these different commands in a moment, but I can add this to the repository and make a simple commit. And now I have a document that is now tracked by version control in this very simple Git repository. We have a question. Question in Linux, it is git init in terminal of the folder. Yes, so that is in Linux, in any operating system, the commands I'm using will be the same across operating systems. So I typed git init in the directory of in the directory I wanted to turn into a Git repository. That's going to be the same in any operating system that you want to use. All right, so that's a simple way to set up a Git repository on your own computer. But most of the time that you're using version control, you want to be able to share your work with collaborators, or sync your work with collaborators, or just share it with the general public. So lots of times you're going to want to share your work on some kind of remote repository as well. So GitHub is kind of one of the most popular places to do this. So now I'm going to show you how to create a repository on GitHub and also use it locally. So I'm going to go, I can probably close this. So let me go to GitHub. And so if you don't already have a GitHub account, you would need to create one. It is free. If you create one as a student, potentially any academic user, but definitely if you're a student, you'll also have access to creating private repositories as well. But creating public repositories is always free. So assuming you've created an account and have logged in, I can just go to new and create a new repository. I'll just call it git test 2 so it doesn't conflict with the one I just made. It's going to be a public repository. I'm going to include a README, so it's generally a good idea to have a README. So this is just a simple text document describing what your repository is, what the project is that you're working on. If you're working Lots of times, especially if you're working with programming languages besides R, or if you're working with R Markdown, a lot of languages, when you're doing an analysis, it might create a lot of kind of temporary files. So if you're knitting an R Markdown document, for example, lots of times there will be temporary files that get created as part of that knitting. And so there is what is called a .gitignore file that you can use to specify a pattern for different documents that should not be tracked by Git. And so there are templates for different languages. So if I go down to R, this will create a .gitignore file that automatically does not track certain temporary documents that tend to get created by R or R Markdown. All right, so I'm just going to create this repository here. Question, why should we want to clone our GitHub repo to use it locally? Is there any reason for that? Is it mandatory or recommended? So generally, you can't really use just a GitHub repository on its own. You need to have some kind of local repository. So whenever you're working, you should have a local Git repository that you're working on. It's really the GitHub repository that is optional. You generally wouldn't have just a GitHub repository because it's not straightforward how to edit things or update documents if you only have a GitHub repository. GitHub does allow some basic editing, but it's not the easiest thing to use. So assuming you're working on a computer of any kind, you'll probably have a local repository that you're doing your actual work on, and then you want to sync that work to the GitHub repository so that other people can see it, so that your collaborators can get that work. This isn't mandatory. You could only have a local repository, but if you want to share your work, generally you'll have some kind of remote repository that other people can see and pull to their own local repositories. All right, so here is my repository on GitHub. Question, is there some limit to the size of files in the local Git repository? In the local repository, there is no limit. GitHub, I think, has a limit on large binary files. So one thing that I will say is that Git and other version control systems are designed primarily for text documents. So code and Markdown and things like this. These version control systems are not designed for large binary files, by which I mean things like images, videos, data sets that are not in a text format, so things that are in like a CSV or tab delimited formats, those are fine. Those are text formats. But things that are in some kind of non-text, some kind of binary formats, Git does not do well with binary files. So generally, you should be just tracking text files in version control. It's sometimes okay to have small binary files like some images here and there, but you don't want to have a huge data set in your Git repository. So generally you would want to either, if you have you can choose what files are actually tracked by Git. So you can have a large data set in your repository locally, but isn't actually tracked by Git so that it won't get pushed to GitHub when you sync with GitHub or things like that. So there's no limit locally. GitHub, I've never reached a limit on GitHub, but there is a limit on binary files. So again, things like images, large data sets, things like that. All right, so here I have a simple repository on GitHub. If I want to clone this to my computer, I can just copy this URL. And let me go here, and I can, let me go. Now I can do git clone and this URL, and this will clone that GitHub repository into a local repository on my computer. So now I can see there's a git test2. I can go look at that. I can see right now the only thing there is the README document. All right, so this is how we can create a GitHub repository as well as a local one. All right, so now as for how we actually use Git and GitHub, there's a few things that it's helpful to understand in terms of how Git works. So you have your working directory. This is just the directory or folder on your machine where the repository lives. Git has this thing called a staging area. So the staging area is the set of files that have changed since your last commit that you want to be part of your next commit. So whenever you make changes, before you can commit them, you have to add them to what is called this staging area. You have your local repository. So this is just the repo on your own computer. And you might also have a remote repository. So this is another version of the repository on a remote site. So GitHub is the place that this would usually live. So a standard Git workflow, you make changes in your working directory. You edit code, make whatever changes you want. Then you would add those changes to the staging area. So you add whatever files you changed to the staging area. When you're satisfied with all of that, with the set of changes that you've made, you can do a commit, and then all of the changes in the staging area get turned into a commit. So essentially a snapshot of the current state of your repository. So at that point, you have committed on your local repository. And then you can push those changes to a remote repository. If your collaborators have made changes and push them themselves, you can pull those changes from the remote repository back to your own local repository. So let me go ahead and so here I'm just going to create a simple text file. Oops. So I have a new text file here in my Git repository locally. And so if I want to add this to the staging area, I can do git add the name of that file. Now I've added it to the staging area. There's a useful shortcut for adding any files that have been changed. So you can do git add --all as a useful shortcut. And now if I want to commit this change, I can do git commit. I can use the -m option to write a short comment. If you don't write a short comment like that, doing a commit will automatically open a text editor where you can enter a longer commit comment. So it's always good to provide some sort of description of what the commit is doing. I've added test.txt. And now I've created a commit. So git add to add that file to the staging area, and then git commit to actually commit those changes and create a snapshot, essentially. Looks like there's another question. Looks like Sai is answering that question currently. Okay, so we've committed we've made a commit, and now we want to push this to the GitHub repository. So we can use git push to do that. So I'm going to do git push. We can have different names for different remote repositories. Kind of the default name is called origin. Origin is kind of the default name for a remote repository. So that's why I'm saying git push origin. And then I specify the name of the branch. So this will usually, by default, you'll have one branch. It'll either be called main or master. So in older versions of Git and GitHub, it defaulted to master. More recent versions call the default branch main. So I'm going to git push to the origin. So that's going to be my GitHub repository. I'm going to push the main branch. And so now I'm pushing any recent commits to GitHub. And if I go back over to GitHub, let me refresh. And so now I see I have this test.txt document now on GitHub. So there's a question about being able to ignore certain files or folders. And so that is through this .gitignore file that I briefly mentioned earlier. So I'm going to go look at this file now. So the .gitignore file just stores all of the different, it's just a place to type the patterns or exact names of any files or patterns of files that you want Git to ignore and not track. So for R, this would be things like your history, any R data files, .tar.gz. So this is an output if you're building a package. The project file that contains your user information and preferences. Vignette outputs, so the HTML or PDF output from our Markdown documents and things like this. So you can include different patterns of specific files that you might want to ignore. So things like PDFs or JPEGs or things like that. And so that's a way that you can ignore specific files that you don't want Git to track. So the way that we generally work with Git and GitHub, we have a local repository, a remote repository that lives on usually a GitHub server, and then our collaborators have their own repositories. So we make changes on our local repository, we push those to a remote repository, usually on GitHub. Our collaborators would pull those changes to their own local machine, make changes themselves, push those changes back to the remote, and we would pull those changes so that we get the changes that our collaborators have made. The basic commands to get started with Git are just git add. So you've seen that. That is how we add files that have been changed to the staging area. Git add all is a useful shortcut to add any files that have been changed. Git commit will create a new commit, so essentially a snapshot of any staged changes. And then git push and pull to push and pull commits to or from your local repository and the remote repository. And the arguments to git push or pull are just the name of the remote branch. So again, that's usually going to be origin. And then the name of the branch. So again, by default, that's going to be main or master. So a typical workflow is assuming you're collaborating with someone, you want to always start your day by pulling any recent changes that your teammates might have made. So start with a git pull to get any changes that your teammates might have made on GitHub. Then you edit, do changes to your local repository, stage those changes with git add, commit those changes with git commit. And it's a good idea to actually pull again to see if if your teammates have made any additional changes. And then you can push your changes to GitHub with git push. And so this is just the general workflow of working with Git and GitHub and sharing and synchronizing your work with collaborators. One thing to keep in mind is you generally always want to pull before pushing. So that means you want to make sure you have all the most recent changes that your teammates might have made before making changes or pushing the changes that you've made. And that just makes it cleaner. So if your teammates have made changes that conflict with your own, you can fix those locally without causing any issues. We've already spent a lot of time on this, so I don't think I'm going to talk about branches right now. But you can, there's a lot of very useful tutorials on Git and GitHub available online. So branches are just a good way of kind of having different versions of the same repository. Looks like there's a couple questions that I'll get to. So question, if someone else has invited you as a collaborator and directed you to a GitHub repository, is the first step to fork their repository and then clone it? So if they've invited you as a collaborator on that repository, then you don't necessarily need to fork it. So if you have permission from the owner of that repository to contribute directly to that repository, then you can just clone it directly, and you can use their repository directly. If you don't have permission to do that, so if you're working with a larger project that isn't like as close collaborators, then you would start by forking it, yes. If you're working with very close collaborators, say you're working on people within your own lab, then you might work on the same GitHub repository. If you're working with outside collaborators, then you might start off by forking it. Question, can you git add from RStudio? I believe you can. Many IDEs, such as RStudio, have Git and GitHub integration so that you can actually use Git commands from the IDE, such as RStudio. I have actually not used them myself. I believe the TAs have. I think at least Sarah has. So Sarah, maybe if you can elaborate on that, but you can do that. I generally just use the command line version to do that myself. So I couldn't tell you how exactly, but you can do that, yes. Question, can you please provide some resources that you think relevant in order to learn more, go further about using Git and GitHub and the Google Doc afterward? Yeah, I can do that. So GitHub has a lot of very useful tutorials, so I can very easily link those, yes. Question, is it safe to store data on a public GitHub repository? Is it secure? Well, it's a public repository, so as long as you don't mind the data being public, then it's fine. I believe it should be secure from other people making changes or anything like that. It should be secure in that way, but other people would have access to the data. So as long as you're okay with that, it should be safe as far as people not being able to make changes to it without your permission, yes. I believe Sai is also offering a more in-depth answer, potentially. Okay, so we've gone on for a while already. So I'm going to take a short break, about 5 minutes. So we'll be back at in 5 minutes, so that's 17 minutes after the hour. So get up, stretch if you need, or get a drink. I will be back in 5 minutes, and we will continue with our next material at 17 minutes after the hour. All right, we'll go ahead and continue. So, right, so just one final comment on Git and GitHub. So if you ever want to, say, write your own R package, it's a very good idea to have a GitHub repository for that package, and Bioconductor specifically. So many of the proteomics packages, including MS Stats and Cardinal, are hosted through the Bioconductor project. And so Bioconductor, now all of the packages on Bioconductor are using Git and GitHub. And so if you were to submit a package to Bioconductor, you'd have to do that through GitHub. So one more reason it's a very good idea to learn these tools. It's just a generally good idea to use some kind of version control system whenever you're working with a complex coding project. So you can easily keep track of changes and go back to earlier versions of your analysis and compare them and things like that. All right. So let's talk about functions and functional programming. So first I'll review some R basics that I won't spend too much time on, then we'll talk more about functions and functional programming in R. So some R basics, a brief history lesson. So R originally started, or at least was originally inspired by, a language called S. So S was a programming language created by John Chambers at Bell Labs in 1976. The idea behind S was to turn ideas into software quickly and faithfully, specifically for data analysis and statistics. The original name of S was actually going to be Statistical Analysis System or Software, SAS, but that was already taken by another very popular statistical package called SAS. So they ended up calling it S. Bell Labs at the time created many languages named after a single letter. Another one was the C language. So if you're familiar with C, that was also created around a similar time at Bell Labs as well. So S came out of Bell Labs, soon became S+, and S and S+ were a proprietary language for analyzing data. So the issue was, much like, say, something like MATLAB today, S was not a free and open source system, so you had to either pay or have a license or to access and use it. And so in 1993, Robert Gentleman and Ra Sehaka created a free and open source version of S that they called R. R coming next to S in the English alphabet. So R came as a free and open source implementation of S so that everybody could use the same kind of code that they were writing with S and S+, but freely without a license or anything like that. And so the language itself would also be open source, and people would be able to update and make changes to the language more easily. It was created with influence, obviously, from S, but also influences from the languages Scheme and XLisp Stat. So Scheme is a dialect of a programming language called Lisp. XLisp Stat is as well. So XLisp Stat was a Lisp language designed specifically for statistical analysis. And so when we use R, a lot of the way that R works is actually influenced not only by S, but also by a family of programming languages called Lisp. So that's just a little bit of history, and maybe I'll point out where we can see some of that in how we use R and how we program with R. So the R language, as you already know, is a language and environment for statistical computing. It is written in C, Fortran, and the R language itself. So the core R interpreter and things like that are written in C, and most of the packages are written in R. It's designed to be flexible and extensible so that we now have over 10,000 user contributed packages. I think that's only counting CRAN packages. So we have even more, including Bioconductor. I think it's probably more than, at least twice this number at this point. The features of the R language, if we were to describe R as a programming language, it is interpreted. So we don't need to compile R code to get it to run. We can just type it in the interpreter, hit enter, and we get results right away. That's a very useful feature for doing interactive analyses. R is what we call a functional language. So it has an emphasis on writing functions and using functions as opposed to things like for loops in many cases. We'll see examples of that as well. R has what we call dynamic typing, so that variables can store data of any type. So we don't need to declare that a certain variable is only an integer or only a double or anything like that. We can use the same variable names to refer to any kind of data. R has what we call lexical scoping. So we'll talk a little bit about scoping. So scoping refers to when you run an R function, how does R figure out what variable names refer to what data actually? So when you see a name of an object in R, how does R figure out what data corresponds to that name? And R also has actually three at this point, different what we call object-oriented programming systems. Excuse me. And we'll talk about that in a next session. So R has this notion of what we call atomic data types. So atomic data types in R means that we can't really break these data types into any smaller components. So these are the simplest data types that we have that we typically use in R to represent data. So we have characters. These represent string data, so text, different kinds of text data. We have doubles, so these are floating point numbers or decimal numbers. Integers, these store integers. We have logical, so these store Boolean values, true, false, and also missing, or NA. And these four are kind of the most common types that we generally see. There's also raw and complex types. So raw stores just raw byte information. So if you want to work directly with a binary file or something like that, you would use a raw vector to look at that. And complex is for complex numbers, which are used a lot in some fields, but less so in proteomics, and unless you're dealing directly with Fourier transforms and things like that. So we generally use characters, doubles, integers, and logicals to represent data. And R does not typically distinguish between doubles and integers. So R has a notion of a numeric type that can refer to either doubles or integers. So this is a major difference from many programming languages like Python, where doubles versus integers is a very important difference that you have to note in many situations. R, for the most part, doesn't care. There are times that it might be helpful for you to know as a user whether something's a double or an integer, but for the most part, R will not note the difference. There are a number of non-atomic data types in R, so common examples of these are lists. So lists are just a kind of a generic vector that can contain different kinds of data elements, that they don't have to be the same data type. We have arrays and matrices, so these are multi-dimensional objects where every element is, again, of the same data type. So some things that kind of distinguish R is in R, everything, at least those data types that we just discussed, everything is a vector. So R does not really have a notion of scalar types. So when we talk about integers or doubles or logicals in R, these are always vectors. So we don't really have scalars in the sense of a single number or a single Boolean value, we're always dealing with vectors. And whenever we use something that looks like a scalar, it's really just a length 1 vector. And this makes R very flexible when it comes to working kind of natively with vectors and matrices and things like this. Standard arithmetic operations like multiplication, division, addition, all of these are all vectorized. So if you have two numeric vectors and you add them or subtract them, those operations are vectorized so that they're applied to every element of those vectors, and the result is also a vector. It's like there's a question. What is the difference between matrix and array? So a matrix is 2-dimensional, an array is any dimensional. So a matrix is just a type of array that has exactly 2 dimensions. So kind of show this specifically. Here, I'll make a 10 by 10 matrix. So A here is a 10 by 10 matrix. So a matrix has 2 dimensions. Specifically, if I look at the class of A, it is actually both a matrix and an array. So a matrix is just a specific type of array that happens to have exactly 2 dimensions. We can create an array with any number of dimensions. So we create an array that just has a single dimension. So B looks like a vector, but it's actually an array that has just a single dimension. We could have a 2-dimensional array, which is a matrix as well. And we could have a 3-dimensional array, and so on and so forth. So array can be any number of dimensions. A matrix is just specifically a 2-dimensional array. We have R natively supports linear algebra, so things like matrix multiplication, singular value decomposition, matrix inversion, things like this through BLAS and LAPACK. And R, as we said, is a functional programming language, so it has an emphasis on a functional programming style. We'll talk a little bit more about what that means in a little bit. So let's talk about functions in R. So there's a quote from John Chambers, the creator of S. This also applies to R as well. So to understand computations in R, 2 slogans are helpful. Everything that exists is an object. Everything that happens is a function call. So we'll come back to some elements of these 2 notions kind of as we go through some of these slides. So everything that exists in R is an object, and everything that happens in R is a function call. So what does that mean? So everything that exists is an object. So in R, everything that exists we can manipulate, and that actually extends to R code itself. And so this is something that's very powerful when it comes to modifying the language and making it more flexible. So we can actually take R code and manipulate that R code, change it. We can manipulate R expressions as objects, as an object itself. This is useful for things like if you've used any of the tidyverse packages, so things like dplyr, ggplot2, they actually rely on this notion that R code and R expressions are an object that can be manipulated. In fact, something as simple as the base R plot. So let me do plot pressure, temperature. So something as simple as the base R plot function relies on this idea that everything is an object in R. So I've specified that I want to plot pressure against temperature from this data set. And something that's kind of amazing is that when we create this plot, R automatically knows that we used the name of pressure and temperature and is able to use these as the labels in this plot. And that applies kind of however we specify them. So let me specify this a different way. And we can see we still get labels that correspond to the arguments to the plot function. And the reason that R can do that is because of this nature of everything in R being an object, including R expressions themselves. This is something that you couldn't really do with a language like Python as easily. There might be a way, but I don't know how. Being able to kind of automatically pick up things like this from the language that you use to just, in this case, create a plot. And so as I said, packages like dplyr and ggplot2 rely on this notion. So if I go over here, so I'm going to go start using some of the R Markdown documents I have. So this is the functions R Markdown document. So let me make this a little larger. So let's consider some simple lines of code, for example. So here we have, we're assigning 2 to x, assigning 3 to y, and then we want to do x plus y. So this seems like a very simple operation. So we're doing an assignment, 2 assignments, and then some kind of addition. And so, but if you really think about what is actually happening behind the scenes in R when we do this, well, I can actually create a language object. So I can use the quote function to kind of just capture the R language expression x plus y. So this is a language object. And I can do things to this language object. I can evaluate it. So x is 2, y is 3. If I evaluate this expression, x plus y, I do what it says. So x plus y, that's going to be 5. So I can evaluate the expression, but I can even actually modify it. So suppose I want to change the addition sign to a multiplication sign. I can do that. So here, if I look at that, I've actually changed the expression, and I can evaluate this new expression. And now x times y, that's going to give me 2 times 3, which is 6. And so the reason that we can do this is because everything that exists is an object. So this is a language object, the first element of which is the operator. So in this case, the multiplication sign. And then we have the names of the 2 arguments. We have a question. Are functions type of and class similar? They are similar. They are not the same. Type of is kind of a bit lower level than class. So type of will give you kind of a lower level information than class does. So in this case, they might be the same. Okay, in this case, they are different. So this is a strange example, but it does work. So class and type of are different things. So type of will kind of get to the lowest level building block of what something is. So kind of the most base type of something. So the type of this object is a language object. There are different classes of language object. This one is a call. A kind of perhaps simpler example would be to take something familiar like a data frame. So here we have the iris data set. Actually, let me do this with something that'll fit. Let's just go with pressure here. All right, here's a data frame that fits on my screen easily. So this is a data frame. If I want to know what the class of this is, it is a data frame. But if I want to know the type of this, it is actually a list. And so that's because a data frame is built on top of the base list data type. Type of kind of goes to a lower level than class does. Is the simplest way for me to put that right now. We can maybe revisit that when we get to object-oriented programming. All right, so that goes to show that everything that exists is an object, including the language itself. Now let's talk about, let me close that. We don't need that anymore. And how about everything that happens is a function call? So everything that happens, everything that is evaluated in R, anything that can be considered potentially a verb in R is a function call. So that includes all basic operators, including addition, multiplication, even assignment. All of these are different function calls. In many languages, there's kind of a distinction between functions and more primitive operations. So assignment in many languages is not a function. But in R, everything that happens is implemented as a function. So that includes things like assignment and even parentheses. So here, before I get to that, let me show how we can rewrite these operators. So in this case, assignment and addition as function calls that we would normally think of. So normally when we think of a function, we think of typing the name of the function and then parentheses and then the arguments inside those parentheses. So here we have these three lines of code. I can actually rewrite them to look more like the standard function that we would think of. So I can write the assignment operator first, and then in parentheses, the name of the variable and the value that I want to assign to it. Actually, let me go ahead and remove X, remove Y. Let me just clear everything in my workspace. All right, so now I have a clean environment, nothing exists. If I execute these lines of code, I'm really doing the exact same thing that I was previously. So if I look now, I have X and Y, and I've just kind of reordered this to look more like a standard function. So the assignment operator, the addition operator, these are all just standard functions. Well, not standard functions, but they are functions. Because they don't follow the standard naming convention for functions, so they use characters that we don't normally allow as variable names. I do have to quote them using backticks. So anytime that you want R to recognize that something is a name rather than an expression of multiple things, you can quote it using backticks. And so that even means I can create a weird variable name that I shouldn't be able to, something like this. So if I look in my environment, I now have a very badly named variable that in normal cases, you can't use that as a variable name, but R is flexible enough that I can force R to recognize that it is a variable name by quoting it in backticks like this. Don't rely on that for most things, though. In this case, I can do that with these special operators. This is also useful if you want to get, say, the help or documentation page for a special operator. So I can look up the help documentation for assignment operators by using this. Otherwise, that's not going to work. But if you ever need to quote a special a variable name in R, you can do that by quoting with backticks. And so the reason this works is that these are all just functions in R. So they're just using a different style than we would normally expect. So usually we write functions in what we call the prefix notation. So the name of the function comes first and then the arguments. But many operators like addition, assignment, multiplication, we usually using what we call the infix notation, where the name of the function comes between the arguments. Another example of an infix function would be the in operator. So the in operator is another function that we usually use as what we call this infix style, where the name of the function comes between the arguments rather than before them. And so this is why, for example, we accessed let me get this again. So this is why, for example, we accessed the operator or the function name as the first element of this language object rather than another one. So that is why when we turn this into a list, the operator, so the name of the function, comes first. And so everything in R is a function that even includes things like parentheses. So I can actually redefine parentheses to do something like this. So this is obviously something that you really shouldn't do, but this shows you that even parentheses are a function in R, and we can actually redefine even what parentheses do. I want to get rid of that though, because you don't want to do that. So functions in R are what we call first-class citizens. So that means they're objects like any other kind of objects. We can assign functions to variable names. We can manipulate functions. And functions have what we call an environment. So when you talk about a function in R has three components. It has the formals. So these are the named parameters of a function. We have the body. So this is the code that is actually evaluated when you execute a function. And then every function in R also has an associated environment. This is a feature of kind of a functional style programming language that not all programming languages will have. So a function in R carries an environment with it that tells the function where to find those variables. Question, are parentheses and curly braces different functions or synonyms? I believe by default, they do the same thing. They might have a different order precedence, but I believe they in most cases do a similar thing. They both will just return their result essentially. Beyond that, I'm not sure. I would have to ask someone like Luke Tierney or something. But for the most case, you should not do something like redefine parentheses or curly braces. All right, so let's define a very simple function. So we're going to define a function called add. So to define a function in R, we use the function keyword. And then in parentheses, we have the names of parameters. And then following that, we have the body of the function. So this will just be the code that is evaluated whenever we call that function or whenever we use it. And then we assign that function to a variable name. And so if I wanted to use this function, I could call it like this. So add 1, 2. So 1 gets, when I call it like that, 1 gets assigned to X, 2 gets assigned to Y, and then X plus Y happens. So we're already a little bit behind on time, so I'm going to skip asking you to write this function yourself. And here's just an example of a function that we'll be using a little bit later. So here's a simple function for imputing missing values in a vector. So I've called it impute NA. It uses if else. It takes a single parameter X. So if else checks wherever there is a missing value. If that is true, if it's missing, it will replace it with the median value of X. Otherwise, it will replace it with the corresponding element of X. So as an example, let me So here's a simple example. So the median of this vector is 3. Impute NA replaces the missing value with the median, which is 3. So we'll come back to the environment notion in a moment. So why do we want to write functions, kind of speaking generally? So the reasons that we might want to write a function as opposed to just having a script that does whatever that function might do is to avoid duplication. So if you have a sequence of R expressions or a script that you use a lot to do kind of similar things, you might find yourself in a situation where you're copying and pasting that code and just changing the data that you're giving it. And that's not a good pattern to have. You don't really want to be just copying and pasting code and having to change a bunch of little things. So writing a function is a good idea because it allows you to avoid that kind of duplication and just use that function instead of copying and pasting code. Lets us easily use common workflows like this. And conveniently, it also lets us share that functionality with others more easily. So rather than just providing a script that only works with a particular data set and requiring people to change a bunch of things to make it work with something else, we could write a function that makes it easier for people to just change the parameters and then have that function work correctly with those new arguments. So kind of as an example of this, if we wanted to impute missing values for different columns in a data frame, without writing a function, we might do something like the top example of this code here. That's not a great way to do this because we're copying and pasting this code. We have to change all of these different arguments for the different column names. So this is not a good way to do things. So the bottom version is a much simpler way of doing this. In fact, we'll learn in a few minutes a way to simplify this even further so we don't have to do this, so we don't have to copy and paste this code at all for the different columns. But here we've simplified things dramatically so that we can just call this impute NA function instead of copying and pasting this code above. So this is the function that we just wrote. So what makes a good function? So when we write a function in R, we kind of want to think about how to write a good function. And so some of the things that go into thinking about how to write a good function is whether it is obviously correct. You want people to be able to read your function and see that it is clearly doing what it should be doing. You want to be able to come back in 6 months or a year and read your code and be able to understand that it is doing the correct thing. Good functions tend to have a very specific and simple use. So when you have a function that tries to do many different things at once, a function that tries to do something too complicated, it can be harder to use that function. It can be a lot harder to write that function as well. So lots of times you want to write functions that do very specific, simple things. And if you need a function that does something more complex, try to break that up into smaller pieces and write those as separate functions, and then have your more complex function just call those other functions. So the simpler, generally, the better for a function. You want to write a function that is concise but also readable. So you want to write verbose enough that it's understandable what you're doing, but also not necessarily so verbose that it gets difficult to read. So readability is an important part of writing a function. So again, if you come back in 6 months or a year and read your own code, ideally you have some comments that describe what you're doing, but even if you didn't, ideally you should be able to read your code and understand what you were doing. Possibly the hardest part of writing a good function is naming it. So coming up with a simple, intuitive name is important. You want it to be kind of obvious what your function does by its name, but also not have a name that's so complicated that it's difficult to use. Speed, sometimes. So this is something that we'll talk about later. So you want a function to be fast, but sometimes that's not the most important thing. So we have a question. Question, what do you think about writing functions that incorporate dplyr and other tidyverse functions? They seem easy to read when you are used to tidyverse functions. So that's actually a little bit complicated. So the issue with using tidyverse functions inside of a function is that tidyverse functions rely heavily on what we call non-standard evaluation. So this idea that our code can be manipulated, and tidyverse functions tend to rely heavily on that. They allow you to do these things like use the column names in a dplyr function without quoting them, or provide an expression that just uses the column names without specifying the name of the data frame and things like that. So it allows you to take a lot of shortcuts that are very helpful in interactive programming, but that non-standard evaluation also makes it more difficult to really use tidyverse functions programmatically inside of another function. And again, the reason for that being, it's hard to pass say the column names that you want to use onto a dplyr function, because dplyr won't recognize those names as strings. It would recognize those as the actual names of a column, which might not be what you intend. So tidyverse has kind of its own sublanguage of R for working with tidyverse functions in a programmatic way. It's called tidy eval, I believe. And so if you're doing something very simple, sometimes it can be okay to use tidyverse functions inside of a function, inside of your own functions. But in a lot of cases, especially if you want to make it easy for those functions to adapt to different data sets, different data frames, and things like that, it can actually be harder, and things won't always work as you expect. So to really programmatically use tidyverse functions inside of a function, you kind of have to follow this idea of tidy eval. So there's a package that has its own documentation. You can read about how to use tidyverse functions, getting around this non-standard evaluation thing. So generally speaking, I would actually tend to avoid tidyverse functions inside of functions unless you're doing something very simple that you know won't really change and isn't really affected by that. Let's see, so before we go to functional programming, I have more examples here than I think we can get through, but I want to at least mention anonymous functions. So one feature of R that is common among functional programming languages is functions being a first-class citizen means that in R, we don't actually have to name functions. We don't actually have to assign functions to a variable name. We can use functions just on their own without naming them. So here I have what we call an anonymous function. So I haven't assigned this function to a variable name, but I can use it on its own. This is very useful for when we get to functional programming and use functions like lapply. Let's see. So I want to talk a little bit about lexical scoping. So how R actually finds the values for variables. So let me give you an example here. So I'm going to create a function called add1. This function is fairly simple. It just takes an argument x, and then it adds 1 to x. Straightforward enough. So if I add 1 to 1, I get 2. Add 1 to 3, get 4. Fairly simple. But what if I wanted to write a function that works similarly to this, but instead of adding a constant, a literal that I specify in the function, what if I want to add some variable, say y? So here I'm going to create a function called add-y. So it's clear what add1 does, but what does add-y do? Well, first let's try it. So add y to 1. apparently that's 4. Add y to 5, apparently that's 3. So it seems y is 3. But how does that function know that? And how is it finding y? Where is y? So as we said, every function in R has an associated environment. So if we look at add y, if we look at the environment of add y, we can see the environment for add y is the global environment. So the global environment is essentially kind of the default environment that you work in as an R user. In the global environment, I happen to have a variable named y that I created earlier, and y is 3. Let's say I change that value, so y is 2 now. And if I use my add y function again, well, it reflects that new y. So if I add y to 1, I get 3 because now y is 2. So it seems a little bit interesting. So what really happens is that R is able to find that y from the global environment so that whenever we use the add y function, it finds the y variable that is in our global environment. So why would we want to do something like this? So there are times that it's useful to do something like this. So suppose we want to create a function that allows a user to create a new function that adds some number val to a number. So I'm going to call this function add val. And if it's not clear exactly what I meant by that, we'll see in a moment. So I'm going to create a function called add val. It takes an argument val, or for value, and this function returns a function, and the function just takes an argument x and adds whatever that value was that was passed here to the argument x. So here I'm going to create this add val function. And so add val, this is a function that returns a function, what we would call a functional or a higher order function. And so add val returns a function. So I can use add val 10. This is going to return a function that adds 10 to whatever I give to it. So I'm going to call it add 10. If I look at the code for add 10, the body, I can see the body is just x plus val. But what's val? Where is val? So somewhere there is a val, a variable called val. If I do add 10, it seems to work just fine. So it seems to be finding this variable called val. Excuse me. So this add 10 function seems to be finding this variable called val. So what is actually happening here is whenever we call a function in R, the following things happen. First, a new temporary environment is created. So R has this notion of environments. So environments are essentially just places that store variables. So usually we work in the global environment, so all of our variables are in the global environment. But we can actually create new environments. So here, E, this is a new environment. I can put things in it. So if I wanted to look at E, the environment E has a variable called X in it. Whenever we call a function in R, a new temporary environment is created. Any formal arguments of the function are assigned to the temporary environment. So in the case of, say, add 10 has a formal argument of x. So when I call add 10 1, the 1 is bound to x. So we assign the value 1 to x in that new temporary environment that was created. And then we assign that temporary environment a parent environment that is the function's environment. So what does that mean? So Remember, each function has an environment associated with it. The environment for add 10 is, well, we're not sure exactly what that is. We saw earlier the environment for add y was the global environment. So in the case of add y, let me again do add y of 5. So add y, when I call add y, we create a new environment. 5 gets assigned to x in that environment. The global environment is then assigned as the parent environment of that temporary environment. And so the way that this works is that when we execute the body of the function, whenever R encounters a name, R searches first the current environment, so that would be the temporary environment. So when it sees x, R looks for a variable named x in that temporary environment that was created. It finds an x, which has been assigned, in this case, 5. So x is 5. That works. We move on to y. So when R encounters y, it looks inside that temporary environment for a variable named y. It doesn't find one, so then it moves up to the next environment, the parent environment. And so in the case of add y, that's going to be the global environment. In the global environment, we have a variable named y, and so R finds that and uses 2 as the value for y. So that is how add y works. For add 10, well, we can see add 10 has this strange environment that we're not sure what that is. We can inspect it, so I can use ls to list the variables in that environment. So it looks like there's a variable called val. If I look at what that is 10. So what happened here was when I call add val of 10, so this returns a function. So when I call add val, a new temporary environment is created. 10 gets assigned to a variable named val. That environment becomes the environment for the function that add val returns. And so add val kind of carries that environment with it. So it's carrying this environment that contains a variable called val. And so that way, the function that is returned by add val always has access to this val variable that it's carrying around with it. And so this is a kind of a simple case where that might not seem too useful, but some places where this is used more practically are, say, for example, the spline fun function. So this is a function that returns a function that can perform spline interpolation. So if I called spline fun on 2 vectors, x and y, spline fun would return to me a function, and I could use that function to predict a y for any x that I give it. And that function somewhere has an environment that stores the data that it needs for that spline function to work. And so this idea of lexical scoping, this is what we call a closure, where a function carries its environment with it. And it's very useful for situations like this, where we want to have a function that can return a function that does something useful. So spline fun is one good example of this, where we can return a function that does something useful. In the case of spline fun, it does spline interpolation. Question, a function creates a temporary environment, but if that function is a functional, then that environment needs to stick around to keep the value around. Yes, if so, how can I find which environments are lingering in my workspace? Good question. So a temporary environment is created, as we said, but then if that environment does need to stick around, then it will. So as long as there is something that is using that environment, then that environment will stay around. So in this case, we have since we have, in the case of add 10 uses this environment that was created when we called add val, and so this environment sticks around. If there were no longer any functions or any references to this environment, then that environment would go away. It would be garbage collected and cleaned up and go away. Unfortunately, there's no real way to kind of just find out what environments are kind of sticking around that I know of. But generally R will take care of this and clean up environments that no longer have any references to them. So if we got rid of add 10, then that environment, the next time R collects garbage, goes through memory, frees up memory, does that thing, then that environment will be cleaned up and the memory freed, because I've removed the function that references it. But I don't know of any way to actually see what environments exist, at least through standard R programming. All right, so that brings us to this idea of functional programming. So functional programming emphasizes, as the name implies, functions. Functions basically map some kind of input to some kind of output. The idea behind what we kind of would call pure functions is that functions do not rely on what we call side effects. So a side effect would be something like printing out something to the console, writing out a file, creating a plot. All of these are side effects. In functional programming, we tend to rely heavily on functions that do not rely on side effects. So in a more kind of imperative style programming language like, say, Python, we might have functions that we use only for their side effects. So we use a function that just might modify a data frame. In R, that's not the case. In R, we take a more functional programming style where instead of modifying a data frame, a function would instead return a new data frame that has been modified. So whereas a function in another language might modify its input and not return anything, in a more functional programming style, functions primarily just return something rather than modify something as a side effect. Of course, we still have functions that create side effects. So plotting, anything that creates a plot, we are using primarily for a side effect. But when we talk about a functional programming style, that means functions that we use for the result that they return rather than any side effects that they may have. In this functional programming style, objects are treated as immutable. What that means is functions do not and cannot modify their inputs. So that means in R, whenever we give a variable to a function as an argument, we can be confident that that function can't change that. So for example, in my or actually even more simply, so let's say the subset operator. So if I want to subset iris where species equals, I forget the name of the iris species. So subset iris where species is Virginica. So in R, where we're treating data as immutable, so subset on the iris dataset returns a new data frame that is only the requested rows, instead of modifying the original data frame to only contain the Virginica flowers. So this is the behavior that we expect out of R, that the arguments that we give to a function cannot be modified or changed. And the reasons that this is useful and that R kind of went in this direction in terms of this functional programming style is when we have this programming style where we can do things like assume that our inputs are immutable, that they won't be changed by a function, it makes it easier to reason about the inputs and outputs of a function. And for something like statistical analysis, being able to easily reason about what's happening in our code is something that's very, very useful. We really, really want to be able to know exactly what is happening with our data and be able to trust that if we give a data set to a function, that function is not necessarily going to modify that data set without permission. Instead, it might return a new version of that data set with the changes that it wanted to make. And that's just kind of a safe way of doing things. This functional programming style also means that whenever we have a function, if we give that function the same input, we can always expect the same output. So we are not relying on any what we call state of the program. So a function shouldn't rely on kind of hidden variables that exist in the environment. We kind of saw an example where these functionals, these closures can potentially not do that in certain cases. But generally speaking, this makes it easier to reason when we expect that the same input will result in the same output. All of this makes testing and debugging simpler and easier. It also makes, we'll see later, hopefully we have time, parallelization is more straightforward when we use this functional programming style. So we just talked about functionals a moment ago. So functionals, also called higher order functions. A functional or a higher order function is any kind of function that either takes one or more functions as input or returns a function as a result. So we saw an example of the latter, but the former is probably much more common. So taking a function as input is a much more common pattern that we see in R. So this is the apply family of functions. You've probably seen these in action before. So there's a family of what we call the apply functions. And the idea behind these is we apply a function over every element of a list. And typically, this is the kind of way that we prefer to do things in R as opposed to something like for loops. So we have, say maybe we have a large data frame. We want to apply the same function over every column of that data frame. Rather than writing a for loop that tries to modify the data frame in place, instead, the R way of doing that would be to use an apply function that applies a function to every column of that data frame and returns a new data frame with the result. So an example of functions from this apply family. So here I just have a simple list that I'll use to show these. So we have lapply. This stands for list apply. So I give it a list or anything resembling a list and a function, and lapply will apply this function to every element of the list. So in this case, lapply will sum up every element of this list. So 1, 2, 3 is summed up, I get 6. 4, 5, 6 is summed up, I get 15, and so on. And so lapply just applies a function to every element of a list, and it also returns the result as a list. Another member of the apply family of functions is sapply. So this is a variant of lapply that tries to what we call simplify its result. What that means is rather than returning the result as a list, if it can turn it into an atomic vector or matrix or array, then sapply will try to do that. So in the case of the same operation here, if I call sapply now to sum up every element of this list, sapply will essentially do lapply first, look at the result. It'll see that every element is a length 1 numeric. And sapply will realize it can simplify that into a length 3 numeric vector. So sapply will try to turn the result into some kind of atomic vector, matrix, or an array if it can, rather than leave the result as a list. vapply is a kind of more optimized variant of sapply. So sapply basically does lapply first, and then looks at the result and tries to figure out if it can simplify it. vapply skips the looking at result and trying to figure it out part. With vapply, we have to tell vapply what the result will look like. And so then vapply can figure that out beforehand and save a little bit of time. So as an example here, if we do vapply on this list, my function is sum. Well, what does sum return? We need to tell vapply that sum returns a length 1 numeric vector. I'm specifying it like this just because I think it's a little bit clearer, but really this just has to be a template. This should be any kind of object that looks the same as what sum returns. So 0, 1, 2.13, anything that's a length 1 numeric vector, so a numeric scalar, basically. Numeric 1 just returns a length 1 numeric vector of zeros. And so vapply does the same thing in this case as sapply, but it's able to do it a little bit more efficiently because it knows what the result will look like. And so we saw earlier this pattern of imputing NA over different columns of a data frame. So one way that we can simplify this is we actually saw from an earlier question that data frames are actually just lists internally. So we can use lapply on a data frame and use impute NA. So in this case, we could use lapply on our data frame to impute all of the columns. The result wouldn't be a list rather than a data frame, but it's straightforward to then turn that list back into a data frame. So that is the basics of what we call functional programming in R, this idea that rather than something like for loops or modifying things in place, we take this functional approach of relying on functions that take an input, return an output, and applying those functions over a list or a vector or columns of a data frame and getting a result. All right, any questions on this topic so far? So the next thing we'll be talking about is object-oriented programming. I think a little bit behind on time, so I think we'll skip the break for this and go into our next section on object-oriented programming. Question, is lapply always used for data frames, or does apply also work for data frame contexts? So the question is about using lapply on data frames versus apply. So we didn't talk about apply just now, but apply is a function designed for matrices and arrays. So let me create a simple matrix. So here I have make it a slightly smaller matrix. So here I have a simple matrix. I can apply over the different what we call margins of a matrix. So that'd be the rows or columns. 1 means over the rows. So if I wanted to sum over the rows, I could do that. If I wanted to sum over the columns, I could do that. In this case, they're the same since this is a diagonal matrix. But apply just applies a function over the rows or columns of a matrix, or over different dimensions of an array if we have a n-dimensional array. So the difference between using lapply on a data frame versus apply is that apply actually only works on matrices and arrays. So if you use apply on a data frame, it will appear to work, but what is actually happening internally is that data frame gets coerced into a matrix. And so if you have non-numeric columns, say a character vector of protein names or something like that, then apply, well, if your function doesn't work with whatever columns you have, it won't work if you, and furthermore, when that data frame gets coerced into a matrix, in a matrix or array, every element has to be of the same data type. So if you have numeric columns as well as character columns, ultimately everything is going to get turned into a character. So for example, let me, I do as matrix on iris, the result is a character matrix. So if I try iris, let's try the sum over the columns of iris, well, I get an error because that's not going to end up working. That's a strange error to, strange warning messages to get, but same thing over the rows. So I also can't do something, let's see. And if I do something like class, well, everything's going to be a character. So apply works specifically for matrices and arrays. lapply is for lists. Data frames internally are lists where the columns are the different elements of a list. So that's why if you want to apply over the columns of a data frame, respecting the different types of those different columns, lapply would be better than apply. There's a comment in chat, always struggle applying apply functions on data frames when I need to use two inputs from the same row but different columns. What is the optimal way of dealing with this operation? So let me take a moment to understand that. We need to use two inputs from the same row but different columns. Okay, I think I understand that. So if we wanted to say, well, wait, let's see.
I can give you a little bit more feedback on that. So yeah. I use lots and lots of for loops because I have to do calculations on my data frames per row. So I create a new column and I need to feed it with data that depends on other columns in the same data frame. And I always get messed up trying to apply any of the apply functions, and I actually feel very discouraged doing it. But I think it's mainly because I do not know how to do it properly.
I see. Yeah, so that is one kind of situation where a for loop might be a better approach if you're kind of building up a data frame in the specific situation where each column depends on the previous columns. So that is one case where I think a for loop would be more appropriate. So generally with the apply functions, you want each you would want each thing that you're applying over to be independent of each other. And so if you have a situation where each new thing is dependent on all the previous things, and that is a case where I think a for loop would be more appropriate, and the apply family might really not be for that specific purpose. So that I think that would be why you would be having trouble, is that is a case where I would use a for loop, I think.
Okay. Thank you. At least I'm not crazy.
Question, would mapply work for that? So based on what we just heard, I think mapply would not work. So mapply is a function that lets us apply over multiple lists or multiple vector-like things at once. And so as an example, let me have so here I have an X and a Y. I can do mapply, let's say addition X and Y. And so mapply, I can give it these two lists, X and Y, the addition operator. So that means I'm going to do element-wise addition over each of the corresponding elements of X and Y. This is a strange warning message I get sometimes. I don't know why I get this. It has nothing to do with what I'm doing right now. Maybe let me turn off simplify. So this is what mapply does. I don't think it applies to the situation that was specifically stated, since if you still can't do this, can't easily do the situation where each element depends on previous elements. So if you have a situation where you're relying on the output of previous iterations, that is a case where a loop is going to be more appropriate. The idea behind the apply functions and these kinds of things is that each thing should be independent of each other. Question, it deserves to be mentioned that many old concerns with for loop performance-wise have been addressed by R internally in recent versions. Another reminder is that if avoiding for loops costs more time, effort than writing the for loop, then you're not making any gains. Yes, so that is something that we will hopefully get to talk about in a little bit when we get to performance in R. So avoiding for loops is not necessarily the correct thing to do in all cases. And that's the situation we just talked about, I think, is one of them. So there are many cases where a for loop is in fact appropriate and the correct thing to do in R. If a for loop makes more sense, then you should use it. In the case where an apply function makes more sense, then use that. And again, the idea behind these apply functions is to make it easy to apply the same function over every element or column of something and get a result from that. So again, we'll revisit some of that when we get to performance, hopefully soon. All right, so I'm going to talk about object-oriented programming in R. First, what is object-oriented programming? And we'll talk a little bit about S3 and S4. I'll probably skip over a lot of the S3 stuff to get to S4, which if you're using bioconductor packages is a little bit more pertinent. So to go back to that quote from John Chambers, everything that exists in R is an object. In addition to that, every object in R has some kind of class associated with it. We saw a little bit of that from the earlier question about the difference between class and type of. So an object's class basically describes the kind of data that it represents, that it stores, but a little bit more than that. Functions, some functions are also able to specialize themselves for different classes. As a simple example, let's take our plot function, the standard base R plotting function. These are three different versions of plot that are essentially doing the same thing. So if I call these different versions of plot, I get essentially the same plot, but in slightly different ways. And so what is actually happening is that these are actually using three different versions of the plot function. So plot is able to adapt to different kinds of arguments that it gets. And the reason for this is R's object-oriented programming system. So object-oriented programming, or OOP, is just a way of organizing data and code. And it's built around the concepts of what we call class. So this is a definition for a kind of object, that kind of data that an object stores and how it's organized. An instance is just a specific case of an object of a particular class. So for example, the iris data set is an instance of a data frame. And then we have what we call methods. So methods are specialized functions that are specialized for a particular class of object. So what we see here are actually three different methods of the plot function. So why learn about object-oriented programming, or why use it? Well, if you've done any kind of programming in R, you've actually already been using R's object-oriented programming systems. So some examples of classes in R are the data frame. So anyone who uses R, I'm sure, uses data frames extensively. So a data frame is an example of a class. that has methods defined for it. The matrix class, both in base R as well as the capital M matrix and the matrix package are classes. And then on bioconductor packages make heavy use of what we call S4 classes we'll talk about. So things like summarized experiment, the capitalized version of data frame, these are all classes in bioconductor packages. And every object in R has some kind of class. So different features of an object-oriented programming system. We have classes. So a class is just a blueprint for organizing different kinds of data. So for example, a data frame is a class. It's a class that stores tabular data organized in rows and columns, where each column is a single data type, but different columns can be of different data types. And what we call an instance is just a specific object of a class. So for example, the iris and empty cars datasets are specific instances of the data frame class. We have what we call inheritance. So we can have parent and child classes. So child or subclasses can specialize the behavior of parent classes or superclasses. So an example of this, if you've used the tidyverse, you're familiar with the tibble. A tibble is just a special kind of data frame. So a tibble is a child class or a subclass of the data frame class. And so the tibble inherits most of its behavior from the data frame class and the way the data frame class behaves. And lastly, we have methods. So a method is just a specialized function that is specialized for a specific class. So we saw this with plot. So plot is what we call a generic function, and there are different plot methods for use with different classes. And the object-oriented class system takes care of finding the correct method whenever we call the plot generic function on different kinds of objects or different classes of objects. So to elaborate on this a little bit, this notion of generic functions, if you've used object-oriented programming in another language like say Python or Java, the style of object-oriented programming in R is a little bit different. So R uses a functional programming style of object-oriented programming. So the approach to this is that in other languages, methods belong to classes, but in R, methods belong to generic functions. So in R, we have what we call generic functions. So these are things like plot, summary, even mean or sum. So these are functions that could reasonably have different kinds of implementations or different behavior depending on what kind of object you give to them. So clearly plot, we might want to plot different things. So we want a generic plot function that can adapt and have different methods for different kinds of objects that we want to plot. Same thing with summary. We want to be able to summarize different kinds of objects in different ways. So these are what we call generic functions, and we can define methods for these different generic functions. So we have a default plot method that we use if there's no other specific methods. There's also a plot method for, say, specifically for functions, specifically for linear models, and different kinds of objects. Same thing for the summary function. For example, this is the summary.lm, so the summary method that we use for summarizing a linear model fit by the lm function. And we call methods just like we would ordinary functions. So for example, here we call the plot generic function, and R automatically takes care of finding the correct method that corresponds to the kind of object that we give to plot. So when it comes to object-oriented programming in R, there are actually two separate object-oriented programming systems. There's the S3 system and the S4 system. So these are named after different versions of S and S+. So S3 came from S version 3, S4 from S version 4. S3 is a simpler object-oriented programming system. If you've used Python, S3 is very similar to the object-oriented system in Python to some extent, in that it's much simpler than S4. S3 has no what we call formal class definitions, and S3 is also what we call single dispatch. So S3 methods can only specialize on their first argument. Then we have S4. S4 is a more complex, more formal object-oriented programming system. So in S4, we have formal class definitions. So we have to officially define a class, what a class looks like, how data is organized in that class. And we can also have validity checking methods. So we can check that a class, an object is a valid object of that class. S4 also has what we call multiple dispatch. So we can specialize methods on more than just one argument at once. The difference between single dispatch and multiple dispatch, if I look at the generic function for plot, plot has two formal arguments, x and y. In S3, we can only define a method for the first one. So the plot S3 plot methods can only change depending on the class of the first argument, but S4 plot methods can specialize on both x and y. So we can have behavior that distinguishes between the different classes of x and y. So in terms of using object-oriented programming in R and where these two class systems are used before we get into how to use them, S3 since it's a simpler system, it tends to be more common in base R. So data frames are an S3 class. The output of linear models and GLMs are S3 classes. So S3 tends to be more common in base R as well as CRAN packages. S4 is much more common in bioconductor packages. So bioconductor, we deal with proteomics data sets, genomics data sets, all these different kinds of complex bioinformatics data structures. And so with S4, we can have a formal class definition that says, this is exactly what this data structure should look like for representing genomics data or proteomics data or single cell data or whatever kind of data set that we're dealing with. And we can even have methods that check for whether an object is in a valid state or not according to these definitions. So I'm just going to briefly touch on S3 since it is common in base R, but tends to be less common on bioconductor, which is where a lot of proteomics software tends to live. So S3 classes, we don't have a formal class definition. An S3 class is just created by setting the class attribute. So for example, cars, this is a data frame. And if I look at the attributes of cars, so every R object can carry attributes with it. The attributes are just a list of different attributes that you want associated with that object. So the cars dataset has a names attribute, a row names attribute, and a class attribute. And so the class attribute is what is all that defines something as an S3 class. And so cars has an S3 class of data frame, and that's what makes cars a data frame. And this is what is returned by the class function when applied to an S3 object. So we can just set the class attribute to create an S3 object. S3 objects just extend base R data types. So any S3 class is built, on top of a list, a character, an integer, double, some kind of base R type, kind of most commonly a list. And then kind of what defines S3 methods is this very simple naming scheme where S3 methods just follow this naming scheme of the name of the generic and then dot and then the name of the class. And this is really all that defines how S3 classes work. So, for example, I'm going to show you a simple example of an S3 class from a kind of a pet simulator game. So suppose we have an animal class with child classes cat and dog. We can have a generic function called speak. Speak can specialize depending on whether the animal is a cat or a dog. So let me go down. And show you. So here I can create a simple object of an animal class. So structure is just a function for adding attributes to an object. So A is just a list. It's an animal because that's the class attribute. That's all that's needed. Here I can create a function that returns an animal. So here I can create a cat named Mittens, dog named Duke. Again, these are just functions that just return a list with a name of that animal and the class. The way inheritance works in S3 is that it is just a character vector where the superclass comes later. So the most specific subclass is first. So Duke is first a dog and then an animal. We can define a print method. So here, this is what an S3 method looks like. It's just the name of a method. So print is what happens when we just type something on the console and hit enter. So there's the print for a data frame. So if I want to print an animal, I would just do print.animal. This is just a function that'll print out the name. And now I can see that that is all it needs for R to recognize that this is the S3 method for printing an animal object. And we can see S3 methods for different objects. So for example, fitted is an S3 method for extracting fitted values from a model. We can see different fitted methods here. Same thing for residuals. So these are different methods for extracting residuals from different kinds of models. We can see all of the different methods for, say, working with a particular class. So the LM function for fitting a linear model returns an object of class LM. And these are the different methods that we can apply to an object of class LM. And this is really all that there is to S3 objects. So for example, residuals.lm is the S3 method for extracting residuals from an LM object. Here I can define a new S3 generic function. Again, I'm going a little bit quickly here since I know we're low on time and I want to talk about S4 classes. And so here we have 3 or 4 different speak methods. So there's a default one. So this is a fallback if there's not a more specific method. So here I'm going to create these 2 animals. If I call speak on the cat, it'll say meow. If I call speak on the dog, it'll say woof. If I call speak on something that isn't an animal, it'll fall back to the default method, and in this case, print weird noises. So that's the S3 class system. It's fairly simple and straightforward. But I want to talk a little bit about S4. So S4 is very commonly used in bioconductor packages. So if you use bioconductor, so things like the very good MSN-based package, the summarized experiment package, the delayed array package we'll hopefully talk about if we have time. These are all S4. These are all packages that use S4 classes heavily. And so it helps to be a little bit familiar with how S4 classes work when using bioconductor, especially if you ever want to author and submit a package to bioconductor. So S4 classes have some kind of formal class definition. we can create a class using the setClass function. We have to define different slots of specific data types. So unlike S3 classes, which are just built on a built-in R data type like a list or a numeric vector, in S4 classes, we have specific slots that we can name. And these different slots, we can also specify that they have to be of a particular data type. And then we create methods for S4 classes with the set method function. So as an example here, so some examples of S4 classes you may be familiar with or might have used. The summarized experiment object from the summarized experiment package. So this is a package and data structure that is used for many experiment types on bioconductor. The MSN base package. So this is a package used for working with mass spectra data in R by Laurent Gatto. And so this is an MSN set. So this is an S4 class from the MSN base package. Delayed array is another S4 class for working with large data sets. There's a capital data frame package from the S4 vectors package on bioconductor as well. So this is just an S4 version of a data frame. So if I want to create an S4 class, I can use the setClass function to do that. I specify the name of the class. Contains means what are the parent classes. So in this case, animal. I don't want to allow objects to be created that are just animals. So I'm going to make it what's called a virtual class. Virtual means that we can't actually create objects that are just this class. The slots here, we're just going to have one slot. It's going to be the name of the animal. And this is going to be a character vector. And we can even have validity checking for S4 classes. So this is a simple validity function. And all it does is it checks that the length of the object name is 1. So with S4 classes, we can access the slots using this @ operator. But this should only be done when you're actually the author of that class or when you're implementing methods for that class. When you're using someone else's S4 class, you should go through what we call accessor methods or getter and setter methods, rather than using this @ accessor directly. So typically, more complex S4 classes like MSN set or summarized experiment will have specific functions that you can use to access the slots. And that's a safer way of accessing them than using this @ operator. So here I'm going to create, So here I'm going to create an animal class in S4, a cat and a dog class in S4 as well. So cat and dog inherit from animal. To create a new S4 object, you can use this new function. I'm going to wrap that in a function that we define for a constructor. And so here I have simple S4 instances of cat4 and dog4. Now, if I want to create an equivalent of the print S3 method we made earlier, I can set a method for the S4 show method. So here is how I can create an S4 method. I use the set method function. I give the name of the generic function, so in this case, show, the name of the class that I want this to be a method for, and then the function that is to be executed for that method. So now if I print out Mittens or Duke, I can see it uses the show method that I just defined. Here I'm creating a new generic function for speak. And here is my speak methods for cat and dog. So if I want to do speak on these, this is how we can use an S4 method for these. All All right, so for the sake of time, I don't want to spend too much more time going into more detail about that unless there are any specific questions. But I wanted to at least give a brief overview and kind of a quick crash course in what object-oriented programming is in R, where you will see it, and at least give you a really brief example of how this works in S3 and S4 specifically. So if you want to see a more in-depth example, I do have an example package on GitHub. So it's called MS Example. This is a GitHub repository that contains a complete R package. That is a very simple package for working with raw mass spectrometry data. And you can look at this as an example of a simple basic implementation of an S4 class for working with a mass spectrum. So I'll just quickly show this to you on GitHub. So here is what this MS example package looks like. So this is what an R package looks like if you haven't looked at the source code for one before. So I have an R directory that contains the R code. This man directory contains documentation. Test contains unit tests. Vignettes contains vignettes in R Markdown format. So I'm going to go look at the R code. Look at mass spectrum. So this is a simple S4 implementation for a mass spectrum object. So I've created a class called mass spectrum. Vector is a class from the S4 vectors class on bioconductor. So mass spectrum is going to extend this vector class. It has slots for the mass to charge ratios or MZ values. This is going to be a numeric vector. Intensities is also a numeric vector. We have a slot for a logical value for whether this mass spectrum is centrated or not, and a slot for peaks. So this will contain the indices of which of these are peaks in this mass spectrum. So if we want to do peak picking, we can store the indices of the peaks here. And so you can take a look at this for some further examples of some an S4 class and some S4 methods that I have defined on it. All right, so I at least want to get to our next topic and talk a little bit about performance in R, and a little bit about debugging if we get there. So let's talk about performance in R. Looks like there's a question. Question how to import use code from GitHub to R. Good question. So let me go to where I just was. So there's an instructions for how to install this both on the GitHub page as well as on the slide that I just got rid of. But there is a package called remotes. If you don't already have the remotes package installed, you can install that just using the standard install.packages. The remotes package lets you install packages from remote repositories like GitHub. And so you can just execute this code here to install this package from GitHub to R, and then you can actually load this package just using the standard library MS example. So this is the code that you can run to install this locally. And in fact, that's what we're going to do in just a moment. I'm going to use this package as an example. So talking about performance in R in the time that we have left. So R is sometimes considered slow. I'd argue that's not, while it is the case in terms of pure R code, most R code can be written in a way to be faster. And this isn't purely an R thing. So if you were to compare, say, R and Python, fact is both R and Python are both very slow when we're talking about purely interpreted R or Python code. Where they are faster is where they use native C code or any kind of C, C++, Fortran code. And so both R and Python tend to be slow on their own, but there are ways to write code in R or Python, and we'll talk about R, such that it will be faster. There are a lot of naive kind of ways of implementing something in R that can end up being slow if you don't know what you're doing. And it's always a good idea to benchmark different implementations rather than just assuming one is going to be faster than another. Again, a good example earlier in terms of for loops. So it's kind of a common advice you'll hear to avoid for loops in R, but for loops are not always slow. In fact, there are times when a for loop will be the correct choice. So generally speaking, before I even talk about performance, you want to avoid premature optimization. So first, we want to write correct code, make sure that your code is actually doing what you want it to, and you're getting correct results. And in most cases, frankly, that will be fast enough. So one of the major advantages of R is that it's generally very quick and easy to write most forms of analyses. Oftentimes, the major time sink is not in waiting for code to run, it's in figuring out how to do something in the first place in a fast way. So with R, it's simple to use your time wisely. Takes not too much time to write something in R and then let it run overnight if you need to while you go and do other things, run experiments in the lab, whatever you happen to be doing, and then come back and it'll be done. As opposed to trying to spend your time trying to write something in a faster language like C or C++, that will tend to take more time, or spending a lot of time trying to figure out how to make something faster in the first place. So first focus on doing something correctly. Lots of times letting it run, even if it takes a while, is still going to save you the most time in the end because you can spend that time while it's running doing other things. In general, beware of naive or early optimization because sometimes it's not warranted. Sometimes things are fast enough already. But especially you want to benchmark to confirm, is something actually slow? What is the actual bottleneck here? And is the implementation that I think will be faster actually faster or not? So a small case study we'll be using here is finding local maxima. So this is going to be part of a peak picking algorithm on a mass spectrum. So I'm going to use that MS example package that I just showed you. So if you want to install this, you can use the instructions on that GitHub page. So install_GitHub function from the remotes package. And then if you have it installed, you can load this MS example package just like a normal R package. So I'm going to use one function from this called simSpectra. This will just simulate a, it's going to be 100, but I guess it'll be 200 mass spectra, which is why I'm setting a seed. Let me restart my R session since I have MaldiQuant loaded, I believe, from loading MSNBase, and both packages have their own mass spectrum classes. All right, let me do that again. I'm going to set a seed since I'm doing a simulation, so that relies on random number generation. So this will make, setting a seed will make this reproducible. So S, this is a list of 200 individual mass spectra. So I can take a look at the first one, the second one, and so on and so forth. I'm going to plot the first one here. So this is the first mass spectrum in this list of 200 mass spectra. And I'm going to write a function for finding a local maxima in a vector. And so the idea being I can use this locmax function as part of a peak picking algorithm. So what this locmax function does is I give it a numeric vector. I give it a window by specifying a half of the window. And to briefly describe what happens, this locmax function will go through the entire vector, sliding the window along. At each point, it will look at the central element in that window. It will see if that central element is larger than all of the other elements in that window. If it is, then it will call that a local maximum. So here I'm going to specify where I'm starting and ending in terms of where I'm looking through this numeric vector. I'm going to initialize an output. So out is going to be an empty integer or length 0 integer vector. And I'm going to be adding the indices of where I find local maxima to this. Firstly, if the vector is too short, I'm going to return without doing anything, because if the input is smaller than the window that I'm looking in, I can't really do anything. Then I'm going to have a for loop. I'm going to loop through this entire vector. I'm going to look at the window that I'm looking at. I'm going to start by saying, setting that this is a local maxima, and then I'm going to look through each individual element inside of this window, each of the intensities inside of this window. If I find any intensities that are larger than the central one that I'm inspecting, I'm going to set isMax to false because it's not a local maxima in that case. If it's still a local maxima after doing that testing, then I will take the current index I, combine that with the previous local maxima indices that I found, and assign that to the new out vector of indices of local maxima. Then at the end, I will return this. So this is my first attempt at this local maxima function. So if I just kind of run this, this will return the indices of the local maxima in this first spectrum. Let me I have that. Let me try to quickly well, I was trying to show you where those local maxima were, but there were a bit too many. There was a lot of them, but I'll just say that this works. You can confirm that on your own. So before we do any optimization, it's a good idea to benchmark how fast our function actually is. So I'm going to use a package called microbenchmark and apply that to this function. So on average, this function takes about 9.7 milliseconds, which is not too bad, but considering that we might want to run this function hundreds or thousands of times, we would like that to be faster. Question, can't find microbenchmark on my computer. If you don't have microbenchmark installed, then just install it using install.packages. All right, so we want to improve the speed of this function. So how can we do better? Well, one major issue is that whenever we do this kind of pattern that we have here, so lots of times when you're kind of a beginner at writing R code, you will follow this kind of pattern of having, of starting with an empty list or an empty vector, and then kind of building it up by using the C function to combine the results you have so far with some kind of new result. So You might do this in a for loop, which is the case here. This is kind of a common pattern when you're beginning to program with R. But the problem is every time that we do this, we essentially have to allocate a whole new vector because we're taking the previous vector. We're not just appending something to the end of it because that's not how R works. Instead, in R, every object is treated as immutable. So the C function will return a new vector that is the combination of its arguments. And so the C function has to allocate an entirely new vector, copy all of the elements over. And that's can be a potentially expensive operation if we're doing it every single time that we find a local maxima. So one simple way to try to improve this is to avoid doing that. That should hopefully save us that time of allocating memory each time. So one way we can do this is here, instead of capturing the indices of the local maxima, I'm going to create a logical vector of trues and falses. Initially, it's all going to be false. And then whenever I find a local maxima, I will just set this to true. In this way, this will be modified in place. I will have some kind of logical vector, and I'm just going to update the falses to trues wherever I find a local maxima. And then at the end, I will use the which function to tell which of the elements are true. So which is just a helpful little function that returns the indices of a logical vector that are true. So let me try this version that removes this, this kind of pattern that is common when you're beginning R programming, but is a very memory intensive thing to do. So this is version 2. And there's one other thing that I want to try before we even time these. So we're still using a for loop here. And kind of the naive advice in R is to avoid using for loops wherever possible. So we'll try that. So here I have a version that removes the for loop and replaces it with a call to vapply. So this is a similar operation, but instead of using the for loop, I'm instead using a vapply. And so by the kind of common wisdom in terms of how to write faster R code, this should be faster because we're avoiding a for loop and replacing it with something that is ostensibly kind of vectorized. So before we compare these different functions, let's verify that they're actually returning the same thing. So here I'm just comparing the results of both of these calls to the initial version that I had. And turns out these are all the same, so everything's okay here. So always make sure that your functions, your different implementations of the same function are actually doing the same thing before benchmarking them. If they are not doing the same thing, then there's no reason to even bother. You want to make sure they're correct first. And so now I will use microbenchmark to benchmark these 3 functions and find out which one is the fastest. And so now we typically want to be using the median. So microbenchmark will run these functions many times and take an average. This can be a very, there can be a lot of outliers sometimes with timing, depending on what else your computer is doing. So we would generally look at the median times. These are in milliseconds. So the first version took approximately 9 milliseconds on average. Second version, 4.7 milliseconds on average. And version 3, about 14.8 milliseconds on average. So kind of surprisingly, well, potentially surprisingly, version 2 is the fastest. So version 2 is the one that retains the for loop. We've gotten rid of the pattern of using the C function in this way to avoid reallocating that vector every for loop. We still have a for loop though, and the version that we removed the for loop and tried to use vapply instead actually ended up being the slowest. And so this kind of just goes to show that it's always important to actually benchmark when you're trying to iterate through different implementations of a function, because sometimes the common wisdom is not accurate for all implementations. So in this case, a for loop is actually the fastest version, although we do want to at least avoid allocating extra memory where we don't need to, because that is going to be very time consuming. So in this case, version 2 was the fastest. So to kind of summarize some general tips in terms of kind of what I was looking for and how to write faster R code is, well, wherever possible, use functions that call down to C or C++ code, because these C and C++, any native code that is compiled will run much faster than interpreted R code. So wherever possible, if you're able to use a function that does this, that's going to be preferred. So a simple example, let me create some kind of matrix. So here I have a matrix. If you just wanted to get the mean of the rows of this matrix, you might do that using the apply function. So this will give me the means of the different rows of the matrix. But this apply function is going to be doing all of that in interpreted R code. When in fact there is a row means function that will do this much more efficiently. Let's see if I can even see this, if I can actually see this, even though this is a very small data set, but still I can see how much faster using a function like row means that calls down to native C or C++ code instead of using the more general apply function here that will just do this mostly in interpreted R code. Question, if you run an R function that calls C code, do you have to install C? No, the C code is compiled for your operating system already. So whenever you install a package, that's all, you don't have to do anything further. Once you install a package that has C code compiled in it, you don't need to install anything special for C, no. That is automatic whenever you work with R. You don't need to. Question, can you still run it if you don't know anything about C? Yes, so you don't need to know anything about C. So these are just recognizing that some functions have a very specific use case. And so they have been optimized for that use case. And usually that means that they have been written in C or C++ to be more efficient. And so one way to kind of notice where this is the case is row means. This is a very specific function that does a single thing. There is a call to the .internal function whenever you see a call to either .internal, .external, or .c or .call. These are indicators that a function is using native code somewhere. But beyond that, you don't need to know anything about C. But generally, the more specific a function is, the more efficient it's going to be at what it does. So apply is a very general function. Row means is a very specific function, so it's more optimized for that specific thing. We want to, generally when we can, use vectorized functions rather than loops. So using the sum function or the mean function, for example, rather than actually using a loop to do that. And avoid creating copies or duplicating objects wherever possible. This is a complicated thing that we could spend a lot more time talking about, but unfortunately we're just about out of time. But one example that we saw in the example here is to avoid, for example, this kind of pattern where we're trying to combine and build something up from scratch, kind of combining results iteratively. It's always better if we can either allocate something beforehand and just assign into it where necessary, or return a result from a vectorized function like vapply or sapply. Question, same applies for R functions that call Python. So Python is also an interpreted language like R. So if you were to use an R function that calls Python, you do need to have Python installed for that. There are far more functions in R that call C than call Python. R functions that call C, you really don't need to know anything about them. For R functions that call Python, you do typically need to have Python installed, and you will be aware of that. And furthermore, and that will typically be used for using libraries that are specific or easier to use in Python, like maybe TensorFlow or something like that. Just calling Python on its own would not guarantee that anything is faster, because Python is interpreted like R. All right, so I don't want to take up more time, since that's the end of my time, but there are some more slides if you want to go through the material on your own, some information about debugging R code, as well as another set of slides and R Markdown describing scalability in R. But for now, since that is the end of the time slot, I'm happy to kind of stop now and take any questions and maybe elaborate further if there's anything that people want me to talk about a little bit more kind of as time allows. So thank you so much for, thank you, Olga, for helping to organize all of this. And thank you for my TAs, Sai and Sarah, for helping to answer the questions and everything. Thank you, everyone. I apologize that we weren't able to get through quite all of the material, but I hope that you can go through it in your own time and find something useful from it.
Kylie, thank you so much. And thank you, the TAs, and thank you, the participants. So if it is okay, we can stay on now for a while. So those of you who have questions or would like to know more about particular issues, you can use the Q&A box. You can also raise your hand, and we can promote you to voice and screen share privileges if you would like. So either post questions on Q&A or raise your hand so that we know that we can bring you in. Other than that, you can sign off until tomorrow. So tomorrow we start talking about statistics and MS stats in R. So join us for that. And Sai, Sarah, Juan, I think you can call it a day for now. Thank you very much for the assistance.
Thank you, everyone.
Thank you.
Thank you very much for your time, Kylie. See you tomorrow.
Thank you. So let's see. One question, any suggestions for a book about object-oriented programming in R? So I believe I have posted on the Google, maybe I didn't, but if not, I'll add it to the Google Docs. But the Advanced R textbook by Hadley Wickham is available freely online. So that goes into a lot of the topics that I've covered today. So that is where I would get started with anything that you want to know more about many of these topics. The Advanced R book by Hadley Wickham is very good. I'll make sure that gets added to the Google Docs if it's not already.
Okay, looks like there are no more questions and no raised hands. Don't be shy.
Olga, maybe you can take that question.
Hold that thought until tomorrow. So I think there will be more people who would know how to work with the raw spectra tomorrow or in the next couple of days. So it depends what you mean by treating SRM or MRM data. If you mean in terms of statistical analysis, so we will definitely discuss this tomorrow for the statistics. In terms of raw data processing, I think probably in the next several days, it will become more relevant. So don't go away. So Kylie, there's another question. Do you think it would be possible to create a database search engine using R? Or because it's interpretive, would it be too computationally expensive? I think it refers to searching databases of proteins for identification of MS spectra.
Yeah, so I think I would write an interface to a database search engine from R so that you can search a database from R, but probably I would use either a different language or an existing database search engine for the actual searching part. So I don't think R is necessarily the right language for actually implementing the database search engine, especially because I think there are a lot of existing things that do that. But certainly what you can do in R is R is very good at being able to call and use other languages or work with online web APIs and things like that. So rather what I would do is to write an R package that accesses the existing database search engines. Question, are there any parallel computation frameworks and in-memory computation frameworks in R? Yes, so we didn't get quite a chance to talk about in the scalability section. I was going to talk a little bit about the BioC parallel package on Bioconductor. So there are several parallel packages available for R. In base R, there's a parallel package that comes with R. It's a little bit harder to use than the BioC parallel package. So the BioC parallel package is on Bioconductor. It kind of consolidates a lot of other things that exist in other R packages. So the main thing that this package provides is a BP lapply function. So this works just like the lapply function in base R, but it allows you to parallelize the lapply. And the nice thing about the BioC parallel package is you can register different backends. So there's a serial backend that's a default fallback. And it comes with a SNO backend. So this is a simple network of workstations that is cross-platform, very widely compatible. There's what we call a multi-core backend. So this one is only compatible with POSIX operating systems. So that would be Mac OS and Linux, but it's a little bit faster than the SNO backend. And there are other packages that build on BioC Parallel that allow you to use different backends as well. And there are, I'm going to guess that you might have meant out of memory rather than in memory. By default, everything in R is in memory, but there are packages for working with out of memory data sets. So the ones I would look at include delayed array, HDF5 array, and matter. So again, these are all bioconductor packages. Delayed array is a general package for, it's an interface for working with other backends. So HDF5 array is a specific type of delayed array that works with this HDF5 scientific format. And then matter is a package from our own lab that provides a kind of more flexible interface for working with custom formats. And it can also be used as a delayed array backend, and we're working on a package that more kind of builds on that further.
So maybe I can add that matter was written by Kylie and had specifically mass spectrometry-based implementations in mind. So it actually can read some of the native mass spectrometric formats. So this may be particularly useful.
Question, as a beginner, if I would like to learn from existing code like MS Stats and how it works with data, is there general advice on how to approach the existing code? Well, I would start with the vignettes just to learn how to use the package generally. And then once you have a good idea of how to actually use the package, then you might want to take a look at the source code on GitHub, for example, of some of the functions that you use a lot and see how those functions are implemented. And what you will commonly do when you start doing that is you'll see some function call some other functions in that source code. So you go look at the functions that function called, and from that kind of start piecing together how the package works and how it was designed. So I would start by reading the public vignettes on how to use the package to learn how to use the package first, then decide if you want to look at some more specific functions and then you could look at the source code on GitHub. And I know for a fact that the newer versions of MS Stats should be much easier to read, I think, than previous versions, as there's been a major effort to rewrite a lot of the code base for that. So hopefully for MS Stats, at least, it'll be easier to read newer code from it now.
Okay, any more questions or raised hands? Okay, and it looks like no more questions. So thank you so much for attending today. Please come back tomorrow and Wednesday to talk about MS Stats. So as Kylie mentioned, MS Stats was entirely rewritten in the last year. And so you will learn a lot about mostly the same functionalities, but 20 to 50% of faster than the previous versions. So there have been a lot of progress. But we will talk about this tomorrow and on Wednesday. Thank you so much and hope to see you the rest of the week.